Welcome back for another SuperMagnetMan video. This time we're going to be looking at something I've been doing with my second grade classes for many years. About 20 plus years I've been doing this in school. And one of the things kids really like is if you take a north and a south magnet, they know they attract and stick together. If you take a north and a north against a north, they repel each other and they can push the magnets around on the table. But I wondered, can you make a north pole stick to a north pole? So we'll show you in this example. If I take this south pole facing a south pole and push it to the center and let go, it stays. Or in this case, the two south poles can stick together. And it gives us a very interesting effect, and this is what the kids really like. If I nudge this magnet to the edges, it flies off. And so we're going to take a detailed look at what's actually happening when two north poles are sticking together. So another way of looking at what happens when two magnets are repelling is to take a look at this. And you can see that in the middle, this is where two large repelling magnets are forcing towards each other. And you see right across this middle where the lines of flux are separating, and it starts moving out to the edges and goes out to the edge. This is what you expect to happen. But when they get so close together that there isn't any room for this to happen, that's when we get this demagnetizing effect. So to break this down, I'm going to start with the magnets that I use in class. This is our S1020. It is 25 millimeters square by 2 millimeters thick, or 1 inch square by 2 millimeters thick. And this one is 12.7 millimeters square, or ½ inch square by 2 millimeters thick. This is an N40 grade and an N50 grade magnet. And so they were wondering, is it being demagnetized? Let's find out. We're going to first look at this one under our magnet viewing film. When I put it under the magnet viewing film, you can see that it's nice and smooth across the surface. We have a nice profile there. When I look at the ½ inch square one, I can see the same profile. It's nice and clean. Let's see what happens now when I have them repel. So if I take these two and repel them, that means flip it over so it's repelling, and push to the center, it sticks. And of course it's going to flip off like the other one did. Now let's take another look at the surface of this larger magnet. When we look at that, you can see traces in the middle where it did indeed demagnetize part of the center because the repelling force was strong enough from this magnet to demagnetize parts of that magnet. Now the net result is that it's really not demagnetized, but it did lose some of its strength. Now we're going to look at what happens with the N45SH. So now we're looking at the N45SH. Exact same size magnets, but both of them are N45SH. So I'm going to go ahead and get the middle reading. And the center reading on the large one is reading north 827, and it's reading south in the center of 838, 840, something in that range. Then I'll look at it 2 millimeters away from the surface. I've got a 2 millimeter thick spacer, and I get it, and it's reading about 768, 762, depends on where it's moving. It slides around and moves just a little bit. Now let's look at our 12 millimeter square, or ½ inch square, in the center. 1569, 1570 is what it's reading. So I've got all the readings earlier, and we're going to take a look at what the readings are on the board. Now we're going to take a look at the data. I've already got the readings for the Gauss meter from these individual magnets before we did this. And in the center of this one, it read 840 south. That's what we looked at just a minute ago. If I get 2 millimeters above the surface, it's 768 south. The North Pole in the center, on the underside of it, was reading 827 Gauss. On our ½ inch square, or 12.7 millimeter square magnet, we're reading 1570 Gauss on the surface in the center. And 2 millimeters above that surface is 1240. Now let's take a look at what happens when we push the two magnets together and they actually stick. What's actually happening, we did the readings now, and I take this 1580 math-wise and I subtract the 768 south from the 1580 north, it left me with 812 north. on the top of this smaller magnet. So if I checked it with a Gauss meter, and when I checked it with a Gauss meter, I got 830. Extremely close numbers confirming what we were thinking about and what's going on. On the underside, where it's the North Pole, and this has a South Pole coming towards it, I was reading 1240 south, 2 millimeters above the smaller magnet. Now I take the 827 that I had on this that's reading north, and guess what? When you subtract them, I got 413. Well, getting 413, then I measured it, and I measured 360 to 370. Depends on, it's really hard sometimes with a Gauss meter to get it to settle on exactly the number that you're looking at, but it's very close here, extremely close here. So looking at it both with the numbers and with what we're doing, we can explain what's going on. So let's take a look and summarize what we've learned about this. The first thing is magnetism goes through anything, even another magnet. Now we can shield magnetism, we can shunt magnetism, but when we're shielding it, all we're really doing is redirecting it. When we do this, we're seeing that the magnetism will normally repel, but as it gets close enough, it will just go straight through the other magnet, and that's why it sticks. When we push it to the corner, as you see, the corner field is extremely strong compared to the center, and so it will flip off. Why does this happen, and what are the parameters we're looking at? The biggest thing that we see happening is it's a ratio of size. The larger the ratio between the small magnet and a large magnet, the easier it is to work. The thinner they are, the easier it is to work. So we can work very well with this one. I have one that is 30 millimeters square, and it's 3 millimeters thick, or 4 millimeters thick. So it's a thicker magnet, but it will do exactly the same thing. It will let it sit, and then it flips off as well. And I can go much larger. I have taken magnets like, I could take this magnet and put it on one that's 4 or 5 inch by 6 inch magnet, and it'll go right to the center and stick even though it's repelling. So that lets you see that the magnetism is going through anything, but it depends on the ratio of sizes. If I tried a 1 inch cube and a 1 inch cube, there's no way it's going to work. It's going to do exactly what you'd expect. But if I took that 1 inch cube and I put a 5 millimeter square magnet on top of it and stuck it to it, it'll stick to it right on the center. So with that, I hope you've learned a little bit more about magnetism and saw a little bit of the fun side too. So look forward to the next video. Our next video coming up is on the factors affecting eddy current drag. This is something that's been a big topic for a lot of our customers, and we want to go into big detail on this. Look forward to that video in the next few weeks. Then we're going to be doing one on Hall sensors and magnets, and looking at it from the magnet side of how we can use magnets to get a better result with Hall sensors. Thanks again.